Welcome to our review of continuity in functions with two variables. First, let's recall the definition of continuity at a specific point, which we'll call a, b. A function of two variables, denoted as f, is continuous at the point a, b if the limit of f as x and y approach a and b, respectively, is equal to the function value at that point, which is f of a and b. A useful fact is that polynomials and rational functions are continuous throughout their domains. Furthermore, if two functions, f and g, are continuous at the point a, b, then their sum, product, and quotient are also continuous at that point. Next, let's explore the continuity of composite functions. On the left, we have the domain of f, shown in green, with a point a, b. Applying f maps the point a, b to f of a and b, which lies inside the domain of another function, g. Next, g takes the output f of a and b and maps it to a real number, which is represented on the number line. Hence, we obtain the composite function, denoted as g applied to f. If both f and g are continuous at their respective points, then the composition, written as g of f of x and y, is also continuous at a, b. Now let's look at some examples of continuous functions. For instance, exponential functions and trigonometric functions, such as e raised to the power of x plus y and sine of x squared plus y squared, are continuous everywhere in two variables. This concludes our review of continuity in functions with two variables. Now let's move on to functions that depend on three variables. We'll begin by defining level surfaces. For a function of three variables, each constant value, denoted as k, corresponds to a level surface. Geometrically, this represents a set of points in three-dimensional space where the function takes the same value, k. Let's visualize how a function maps from three-dimensional space to the real numbers. Here, the green rectangle represents a portion of the three-dimensional domain of our function, and a point, which we'll call p, represents a specific location within that domain. Our function f assigns each point, written as x, y, z, to a single real number. Next, let's look at specific examples of level surfaces. Consider the function where f of x, y, and z is given by x squared plus y squared plus z squared. In this case, the level surfaces are spheres centered at the origin, where each constant value, written as c, corresponds to a sphere with a radius equal to the square root of c. Here, we've depicted several spherical level surfaces with different radii. Now let's move on to another example. Consider a function where f of x, y, and z is given by x plus y plus z. In this case, the level surfaces are planes, where each constant value, denoted as c, corresponds to a specific plane in three-dimensional space. These colored planes illustrate different level surfaces, where c is less than 0, equal to 0, or greater than 0. Finally, let's restate the concept of level surfaces and review the definition of a limit in three variables. Each constant value, denoted as c, determines a unique level surface for the function f in three-dimensional space. The definition of a limit in three variables follows the same epsilon-delta criterion as in functions with one or two variables, but now it applies to distances measured in three-dimensional space. This concludes our introduction to continuity, composite functions, and level surfaces in multiple variables. Thank you for watching.